I thought I would illustrate why the chain rule is so useful. This is a partial differential equation, this expression here. So, like an ordinary differential equation, a partial differential equation is an equation that involves partial derivatives, as opposed to an ODE, which involves ordinary derivatives, and we've been studying. A PDE requires a couple of additional conditions to solve completely. We need an initial condition, so that is the state of the system at, for example, time 0, and we also need some sort of indication on what happens to the spatial behavior. So I've euphemistically termed this a boundary condition. We only need one of them, and I'm kind of prescribing two things here because I'm making a statement about rho at plus or minus infinity, both of them. I'm just going to kind of hand wave past that. We need, obviously, these two conditions because we're doing two integrals, essentially, one with respect to t and one with respect to x. Let's just sketch what our initial condition looks like. You may recognize this function. It's called a Gaussian. It looks like a bell shape. Worst Gaussian. Okay, it looks like that. That immediately satisfies this boundary condition. Right, that's why I chose this initial condition, because I know what's going to happen with this equation. We have this blob of stuff localized around the origin, and it tapers off quite rapidly to give us this classic bell curve shape. To solve this partial differential equation, we're solving in xt space. Right, so this is our domain of interest, right? We want a solution from time equals 0 and every possible spatial coordinate. What we do is we reduce our PDE to two ODEs. And we suppose that x is a function of time, x of t. Therefore, rho is a function of time alone. And we can use the chain rule to evaluate the total derivative. What we notice is this chain rule bears a great similarity to our PDE. We've got our d rho dx, we've got our d rho dt, and we have this c instead of dx dt. What we can do by comparing these two expressions, we note if dx dt equals c, then d rho dt equals 0, right? So if this is true, right, then we have our partial differential equation. And this whole thing would be d rho dt plus c d rho dx, which we know is equal to 0. So d rho dt must be equal to 0 as well. And that's it. That's reduced our partial differential equation to two very simple ordinary differential equations. We do have to think about what our initial conditions are. For example, if we were to just integrate this equation, we would find x equals c of t plus some constant of integration d. Now that's a straight line. X is some linear function of time. So we've got, if you like, in our xt space, we've got all these different straight lines. So we call our initial condition x naught. We plug in, we find that our d must be equal to x naught. And what we have here is we can integrate rho with respect to time. We just get a constant. So how do we determine x naught and our constant a? Well, we don't have to determine x naught. X naught's just the starting point of these straight lines. So it's very simple to write x naught as a function of x and t. Rho, we appeal to our initial condition. We see that rho at time 0 equals f of x. But because f of x is a function of x of t, all we do is we plug in our initial x value. So at t equals 0, x equals x naught. So rho naught equals f of x naught equals e to the minus x naught squared. And we find that rho must be equal to this. We know what x naught is. So we simply substitute back in. Oops. We found our solution to our partial differential equation. You can verify that this is the true solution by substitution. You can take this, plug it in there, and you'll find it's equal to 0. The interesting thing about this is if you plot it at different space and time, it describes the initial pulse simply moving in one direction as time increases. So that's an aside. It's not something that's going to be examinable. This is partial differential equation solving. This will come in useful when you see fluid dynamics. This is particularly useful for modeling gas behavior in pipes, for example. It's an illustration of how powerful this little chain rule happens to be. The reason the chain rule is useful is because we don't necessarily always know what x as a function of time happens to be. We just want to suppose that that is true and use the chain rule to deduce what x of t must be. So that's why we learn the chain rule.